In the last video, we looked at using a simple recipe to put together Lewis structures for covalent compounds. In all the examples that we've done up until now, when we got down to step 5, the central atom was just fine. It was satisfied. In this video, we're going to do some where the central atom still isn't satisfied when we get to step 5, and we're going to see what you can do about that. Let's do an example of a molecule that is going to turn out to be like that. How about we do the molecule NP? Okay, so this is a nitrogen hooked to a phosphorus. And let's see what happens when we follow the recipe. Draw a skeleton structure. Well, we've only got 2 atoms here, so that's fairly simple. I should decide, though, what should be the central atom and which one should be the outside atom. Well, it looks to me like nitrogen is on the edge and phosphorus is closer to the center of the table. So I'll put the phosphorus in the center of the structure. It doesn't matter how I write it. Maybe that. Now I'm going to count the valence electrons. Let's look at the column that the nitrogen and the phosphorus are in on the periodic table. There's 5 valence electrons for each of them. So for step 2, this is step 1. For step 2, count the valence electrons. It's 5 for this and 5 for that. That gives me 10. Okay, the next thing I do in step 3 is connect the structure. And that means take my skeleton structure and draw bonds between the central atom and the outside atoms. So there's a bond. Now, that cost me a little bit though. How many electrons did I use up there? If you said 2, that's correct. Every time you draw a stick, that's 2 electrons. So now I have 8 electrons left. As I'm building this Lewis structure, I'm going to be bookkeeping how many electrons I've got left to play. 4. Satisfy all of the outer atoms. Okay, we decided phosphorus is the central one and nitrogen is the outer atom. So now how many more does the nitrogen want? It's got 2, and what does it want? It wants to get an octet. All of the elements, except for hydrogen, in a Lewis structure want to have a total of 8 around them. That's the octet rule. Hydrogen is satisfied with just 2. But this is going to want 8. It's got 2, because the stick counts for 2, and it wants 6 more. Now I've got 8, so I'm going to plunk down 6 more for it, and now it's got 8. It's satisfied. I did satisfy the outer atom, the nitrogen. Okay, the next step is dump the remaining electrons on the central atom. All right, I took away 6 electrons there, and I've got 2 at this point. So for step 5, I'm going to take these 2 and dump them on the central atom. Here's the structure I had. Take those 2 and dump them over here, or anywhere, on the phosphorus. Now I have none left. Okay? 6. Is the 5. Is the central atom satisfied? Well, let's look at it. Here's the central atom, the phosphorus. How many does it have? It has 2 for this and 2 more for that, so it thinks it has a total of 4. It is not satisfied. It does not have an octet. It does not have 8 electrons. It wants 4 more. But where can I get them? I have no more to dump on there. Well, if the central atom is not satisfied at this point, what you want to do is share lone pairs with the neighbors. Now this nitrogen has got a lot of lone pairs on it. If I share that lone pair and make it into a stick, the nitrogen still has that, and the nitrogen will still be satisfied. But now the phosphorus will think that it has 2 more electrons. But how many more does it want? It had 4. If we share 2, that's not enough. It wants to have 8, so I have to share another lone pair. I'm going to share 2 lone pairs. So I'm going to rewrite the structure like this. Now, do you see what happened? I took these lone pairs and turned them into sticks. There was one there, and now I have a multiple bond here. In fact, this is called a triple bond. And there are six electrons, or 3 pairs of electrons, gluing the phosphorus and the nitrogen together in this molecule. So you have a triple bond there. And now everything is satisfied. If I look at the phosphorus, it has 1, 2, 3, 4, 5, 6, 7, 8 electrons around it, and the same with the nitrogen. 1, 2, 3, 4, 5, 6, 7, 8 electrons around the nitrogen. Everything's got 8, it's got an octet, so I'm done. Now, what about these multiple bonds? If you've got a single bond, and you've got a structure with a double bond in it, or you could have a triple bond like we just had, and when you get into a 400 level course, they'll show you that you can have a quadruple bond as well. But those are very rare, and we won't ever see them with the kind of S&P block elements that we're dealing with. But what's different about these bonds? Well, you would guess that a multiple bond would be stronger than a single bond. There's more electrons gluing the nuclei together, and that is true. So this is the strongest of those 3 bonds. And another thing is, the more electrons that you've got gluing the 2 nuclei together, the closer together the 2 nuclei draw. So a triple bond will be the shortest. The strongest and the shortest bond is the triple bond. The longest and the weakest bond is the single bond. So if you're looking at relative bond strengths, a multiple bond, the more bonds you have, the stronger the bond is. The more bonds you have, the shorter the bond is. Shorter is stronger. Okay? With molecules, anyway. Let's do another one. Let's do carbon dioxide. Okay, let's step 1, write the skeleton structure. Well, what should go in the center of my structure, do you think? Take a look at the periodic table. We've got carbon in here, we've got oxygen. Looks to me like the carbon is closer to the center of the table than oxygen is. So I'm going to put carbon in the center of my structure. And my skeleton structure might look like this. That's step 1. Step 2, count the valence electrons. Again, looking at my periodic table, my oxygen has got 6 valence electrons. There's 2 of those. And my carbon has got 4. So I have 6 plus 4 is 10, plus 6 is 16. 16 valence electrons. Okay. Step 3, connect the structure. Here's my skeleton. Going to connect the central one with all the outside ones. And that took away 2, 4 electrons. I've got 12 electrons left at this point. The next thing I'm going to do is satisfy the outer atoms. Now the outer oxygens here, how many more does this oxygen want? Now it wants 8 altogether. This stick means it's got 2, so it needs 6 more. So what I'm going to do is take these 12 electrons and deal them out so that I'm giving each of the oxygens a total of 8. It's got 2, 3, okay, so this is 1, 2, 3, 4, 5, 6. That's satisfied because it's got 8 around it. 7, 8, 9, 10, 11, 12. That's satisfied because it's got 8 around it. But I've used up all my 12 electrons. I have none left. Now, 5th step. Dump all the remaining electrons onto the central atom. Okay, let's dump them onto the carbon. Well, I've got none to dump, so I can't do that. So I'm stuck with this structure at this point. Is the central atom satisfied? Well, it needs 8 to be satisfied, and it's only got 4, so it needs 4 more, but I have no more to give it. So I have to say, no, it's not satisfied. Then what I have to do is share lone pairs with the neighbors. Now there's a couple of different ways that I can do this. It's going to turn out that the best way is to share one there. That'll give it 6, but then I have to share another one. So if I do that, I get a structure that looks like this. Now, is the carbon satisfied? Now it is. It's got 2, 4, 6, 8 electrons around it. Is this oxygen satisfied? Yes. It has 1, 2, 3, 4, 5, 6, 7, 8 electrons around it. And the same thing for that oxygen. Everything is happy, so it looks like I'm done. It looks like that's the Lewis structure. It has 2 double bonds in it and 4 lone pairs altogether. So each one of those unshared pairs is a lone pair, and there are 4 of them. Now, I kind of said, well, it'll turn out that the best way to do it is this way and this way. How did I know that? Well, there is something that we can do to check and see if we're sharing electrons with neighbors properly, because there was another way that I could have done that. What if instead of sharing a lone pair with each of the neighbors, I took 2 lone pairs from one of the neighbors? In other words, suppose, let's back up to where we were. Suppose I had this structure and I was trying to satisfy the carbon. What if I took a lone pair from here and a lone pair from here? That would also satisfy the carbon, and I would be left with a structure that looks like this. Now, I could have done that on the other side as well. What if I would have taken a lone pair from here and a lone pair from here? So I started out with this in the previous step, and I'm trying to satisfy the carbon by giving it 4 more electrons. What if I shared that and that? Then I would have gotten a structure that looks like this. Now there are 3 possible structures that I have right here. And my job next, in the next video, is to pick out which one is the best. When you have a choice about different ways to do it, what you're going to have to do, we're going to see, is do it all possible ways, and then use something called formal charges to pick out the best structure. And we'll see that in the next video.